Maybe now, is it better? Yeah, okay. So thanks for the invitation. It's a great pleasure to be here. So I will maybe start by giving you two definitions in the abstract setting, and then basically the talk will be just about them appearing in smooth dynamical systems. So the first so the abstract setting is the following. So and I'll use T, X, and mu to denote the abstract, so no smooth structure. So T is an automorphism of a probability space. So that's measure preserving map, probability measure here. And then P is a finite partition, a finite partition of X. Okay, and then we can define, so if you have two partitions, then you can define the wedge, P wedge Q. So if P and Q are two finite partitions, then this is just Pi intersection Qj over all the atoms. And then an important partition that appears quite a lot in dynamics. So this doesn't see the dynamics, but if you, quite often you consider partitions of that form. So n to say n prime, TIP. So this now sees the dynamics. So I take the partition P and I iterate it whatever number of times. It can sometimes also n and n prime can be infinity. So for example, the definition 0 would be that P is a generator if like if we take from minus infinity to infinity TIP, so the smallest sigma algebra containing all the partitions TIP, and say here there is some sigma algebra B, if this is equal to B. That's the first definition. And now I would like to move to defining the K property. So this is the first, say, important definition that we will be discussing. So partitions were introduced by Kolmogorov, so K partitions for short. So here's the definition. So a partition P is K is a K partition if for any set D inside minus infinity to infinity Ti of P, and for any epsilon bigger than 0, there exists an n0 that might depend, usually depends on epsilon and the set D, such that for epsilon almost every, and I'll define this, I can define this atom of n prime TIP, where n prime is prime bigger than n, bigger than 0, we have that measure. So for epsilon almost every atom A of this partition, we have that measure A intersection D minus over measure of A minus measure of D is less than epsilon. Okay, and I haven't defined this yet. I forgot. So what does it mean, epsilon almost every atom? So it means that the union of atoms for which it holds has measure larger than or equal than 1 minus epsilon. So maybe a remark. Epsilon, so we say epsilon almost every atom of P, atom of partition Q, whatever partition satisfies something, satisfies star if the union of all atoms of all atoms satisfying this, satisfying star as measure larger than 1 minus epsilon. Okay, so that's the first important. Any question? Yeah, so that's the first definition. It's definition of a partition being K, and maybe definition 2, which is usually part of this definition, but you can split. So we say that T is a K automorphism. If there exists a generating K partition. And then, in fact, it follows that every partition is K, because, I mean, this, for generators, this is as large as it can be, so that's easy to see. Okay, so that's the definition of K automorphism. No, n prime larger than or equal than to n prime. So the future has not much dependence from the past. So like it could be one, just one. Yeah. Usually you apply it to large chunks, but yeah. Okay, and there is a theorem by Rochlin and Sinai. If you are not familiar maybe with this measured theoretic language so much, although as you'll see in a moment, this has a, I would say, a fantastic interpretation in smooth dynamics, this property. There is a theorem of Rochlin and Sinai which says that T being K is equivalent to the fact that every factor of T, every non-trivial factor of T has positive entropy. So usually, I mean, if you don't want to get, this is easier maybe to state than this property, although this one, as you'll see, you can really appreciate it in the context of smooth dynamics. Okay, so that's definition of K, and the other definition that I want to make is that of Bernoulli, so definition 3, T is Bernoulli if it is measured theoretically, so everything is a measure theory, so maybe I'm not going to write it. If it is isomorphic to a Bernoulli shift, Bernoulli scheme maybe. So i.e. a shift on a finite alphabet A to the Z and some probability vector P. Okay, so from the measure theoretic point of view, it is just a shift on finite, on bi-infinite sequences with some probability distribution. These are non-negative numbers and sum up to 1. Here maybe I should put Z. Okay, so this is maybe something I won't be, so okay, I mean there is a, whenever you have a map T x mu, so okay, maybe the simplest way to say it is just an invariant subsigma algebra. So you have your map T has a sigma algebra that it preserves, but the sigma algebra might have subsigma algebras. And every such subsigma algebra that's additionally T invariant is a factor. So this is just, you know, I mean, think of usually maybe the easiest way, if you haven't seen it before, to understand K is just identity times a Bernoulli shift. Then there is a sigma algebra, which is the vertical one, and it only sees the identity, and then it has a non-trivial factor that has 0 entropy. So somehow being K excludes, in particular, products, but it actually excludes a part of your system that would have 0 entropy. Yeah. Okay, so, and equivalently, this is equivalent to saying, there exists what's called an independent generator P, independent generator So there exists, and maybe I'll define what this means. This means, so P, a finite partition, is an independent generator if, let me write maybe something like this, N1, N2, N1, N2, TIP, 3 and 4 TIP are independent. So these are independent. With the right choice of N1 and 2, so say N1 is less or equal than N2, less than N3, less or equal than N4. So basically this means that whatever I see from times N1 to N2 does not have any influence from what I see from N3 to N4. So for example, for a Bernoulli scheme, the partition that you take would be a partition into cylinders, just on the 0th coordinate. This is an example of an independent generator, and you can push it through isomorphism, so it's easy to see that these two are the same. But this has the nice feature, this part of the definition here is, it has the nice feature that maybe an observation is that K implies, sorry, not this way, Bernoulli implies K. Implies K. And the reason is that if you take any measurable set, you can approximate it with, if P is a generator, with a partition like this, up to an epsilon, and then it becomes independent of this partition. So this would be 0, but there is an epsilon error when you approximate D by this one, and that's where the epsilon error comes from here. But this one is the easy direction from the definition. And in fact, I think Kolmogorov conjectured that it's the opposite, that K systems should be as Bernoulli originally, but this is not the case. So yeah, so we are talking about finite generators classically, yeah. Sorry? At this point, no. So I said A is fine. Yeah, A is fine. You could, okay, this definition would be equivalent to just saying infinite with partition, which is a generator in finite entropy, if you want. If you want to reduce to infinite. I mean, have a more general scheme, more general alphabets. Okay, so that was Bernoulli implies K, and then the question was whether the opposite was possible. Is also true, and this is not the case. Theorem 1 is due to Ornstein. K does not imply Bernoulli. And it was the first example, so it was good that such an example was constructed. The problem is that it was really a construction, so I can't define this system for you here, but I can define another one that will be important, that is also K and not Bernoulli. Okay, so that's maybe, we are still in the abstract setting, soon we are going to move to the smooth one, but maybe I wanted to give you one example that is that one can actually write a formula for. So I think theorem 2, which is due to Kalikov, and this was a conjecture, I think, made by Adler, Ornstein, and Weiss, is that the TT inverse map, and I'll define what it is K and not Bernoulli. And here I can define what the map is. So the map acts on, so let's call this map S. It's going to be simpler for me to maybe. So this class of maps is called TT inverse, and it's going to be clear from the definition why they are called this way. But it's not a nice notation maybe to use, so I'll just use S. So S acts on 0, 1 to the Z. times 0 1 to the z with just the product measure. So it's 1 half 1 half the z times 1 half 1 half to the z. So just the space is the product, the system is not the product, so that's why it's maybe why it gets interesting. So the system, what it does, it takes S of xy equals sigma x. So on the first we shift, and on the other one we do a shift, but we do minus 1 to power x0 of y. So this is a skew product over a Bernoulli base, just 0 1 to the z with the 1 half measure. And then in the fiber, we put another Bernoulli shift, but here we don't iterate it forward. We iterate it depending on what the 0th coordinate of the base is. So here is where the interesting thing happens. I mean, this function tau of x is kind of what is the source of this exotic behavior, maybe. The important thing here is that tau has mean 0, right? So that's the important thing. Mean 0. Okay, and this class of systems is called often random walks in random scenery. So the way you should think is maybe we have position 0, and then depending on what we see at x, at the first coordinate we either go left or right, and then at each step we continue. So the itinerary of x will tell us which way we jump, and we jump by a Bernoulli shift. So here you could put many more generals, I mean many other systems, but the one kind of historically that was first maybe considered was just another Bernoulli shift. And the idea is, I mean, just to maybe try to convince you that the system is kind of exotic, is that it has a hyperbolic Bernoulli base, but here, due to the fact that the function has 0 mean, right, we move by root n after n iterates. So basically the window for the fiber is from root n roughly to, after n steps, to minus root n, and hence the fiber does not contribute entropy. On the other hand, it is still quite complicated. So if you count the orbit growth on the fiber, it is like e root n, right? Roughly. I mean, up to, I mean, there is a CLT for this function, for tau. So, you know, there is this Gaussian, but roughly this is kind of the growth. Yeah, so this was maybe the first system where you could write a formula for K and not Bernoulli. Interestingly, if you put a function of positive or negative mean, it will still be Bernoulli. So it's really, because it's basically then a product of two Bernoullis, but the fact that you have mean 0 changes the game quite a lot. Okay, so that's maybe the abstract setting. And now I'd like to move to smooth situation and discuss these two properties in the smooth setting. Yeah. So now smooth setting will mean we have a smooth setting. Means we have, say, f, which is C1 plus alpha diffeomorphism, diffeo, preserving a smooth mu, a smooth measure m. M and this is on M. And then, okay, you can ask, and there has been, you know, this is the setting where there has been a lot of studies. So, okay, you have a smooth structure, but you can ask about appearance or like interactions of these abstract properties. And I couldn't find a reference. I didn't look for long, but I think there was a, I don't want to say Kolmogorov, but at some point I think people thought that smooth systems will have 0 entropy. I don't know if anyone? Huh? I didn't want to mention him because he already said K not Bernoulli and then another. Yeah, but yeah, I was hesitant, but I think, right? So, yeah, so Kolmogorov also thought all smooth systems should have zero entropy, and I think second half of 20th century showed that it's very wrong. I mean, it is different. And basically, I would like to discuss maybe now what happens with K and Bernoulli properties. So K property in smooth setting. And just in the interest of time, in this part, I will skip maybe particular results. I would rather focus on the mechanism that was discovered. Smooth has, wait. Smooth is 2O and 1M, right? Yeah. Okay, sorry. Yeah. So basically, I would just like to present you a mechanism that is used since Sinai. So I think Sinai was, in his work in early 60s, he was the first one to discover this mechanism for proving K property. And actually, I can show you how this abstract property falls nicely into the geometric picture that you have for, say, nice systems. So here what we could try to prove is, I mean, this is essentially, I mean, you can talk about Pinsker partitions and so on, but I don't want to do that. But Sinai's theorem is essentially that K property follows from ergodicity / equidistribution of the unstable foliation. Unstable foliation. So this is where he first, basically, okay, he said that the Pinsker is saturated by U and S, but I think if we want to avoid maybe more abstract definitions, this is, I mean, it is a theorem. Maybe there are some technicalities that I don't want to put here, but I think it's fair to say that this is a theorem. And the idea is very simple. So let me show you, the whole thing is hidden here. So just think of a 2-1-1 map maybe to see this. If you haven't seen it, if you have, then yeah, apologies. But think of 2-1-1-1 map. But you'll see that what I'm saying generalizes to essentially the setting of, say, non-uniformly hyperbolic systems, even more. Essentially, this is the only way that I think is mostly used to prove K still. Yeah, so we have this unstable foliation, and the thing to notice is that if you look at an atom, so here is the definition of K, and the question one should ask is, what is this object, right? This is the object, so this is just a measurable set, so think of it as a ball, right? So D is just a ball somewhere here, right? And then the object that's kind of mysterious is this one, right? So how do the atoms look like? And it turns out that the atoms, so imagine drawing a long unstable, WU. I mean, here it's just a line, but I'm drawing maybe a schematic picture. And then if you iterate, so if you look at the wedge n prime, TIP, with n large, right? Each time you iterate it, because you look at the partition forward, which means you iterate your dynamics backward. So if I take 2 points, say, on the unstable, XX prime, say, each time I iterate backward, they will come back closer. And you know, the picture is it's going to get shorter, and then shorter, and then shorter, and so on. And it turns out that any atom A of this partition needs to be saturated by the unstables. So basically, if 2 points are in one long unstable piece, they'll be in one atom because it's contracted each time I apply the dynamics. So if the n is large, all the pieces will be shorter, and they will be in one atom of the partition, right? So these points, an atom are points which, from time minus n prime to minus n, are in one atom of the partition, right? And we've just shown that the unstable contracts. So unless there is a boundary effect where the 2 points get very close to the boundary of the partition, right? It is easy to believe that they will be in one atom. And then your set A, in fact, is, so the set A, any atom looks more or less like this, right? It's a union of unstable pieces, very long unstable pieces. Right? At least on the pictures it looks nice. You need to work a little bit to make it a proof. And then if you know that each individual unstable piece equidistributes in the space, so each of these long lines will hit the ball with the correct frequency, right? It's exactly, basically now you do Fubini. So you take your set A, it looks like this tube, you split it into the unstables, and you show that for each unstable I have this, so for A being the unstable, just because I assume equidistribution. So that's kind of the proof of K. And I don't know if it's an if and only if, but I think it's close. Okay, so now, of course, yeah. I mean, you need to, so I'm skipping the details because in general, you know, you don't have, not all points have long unstables. You need to, a little bit of passing theory to work. Yeah, so, okay, I'm saying here I should say from ergodicity equidistribution of almost all unstable leaves. So I'm, you know, I'm still saying it is true, but as written, maybe you need to weaken this slightly, no? Yeah, so that's what I'm saying. So the idea is here, and you need to work on it to make it work in the abstract setting. But basically, this is the proof, and then essentially, since it's an if and only if, understood properly, you know, whenever you have a system that has some positive Lyapunov exponent or some non-zero exponent, this is what you want to do. You take the unstable foliation of a typical point, and you want to show it equidistributes in space. And if you do this, you get the K property. And now there are many examples. So, I mean, for example, this is a very easy, maybe trivial example of a system that's K, but there is many more. Yeah, so maybe I'll move to Bernoulli now. Because, yeah. For Bernoulli, the thing is trickier if you want to show Bernoulli. And it seems that there is no, so the nice feature of this theorem is that it's really, you stay in the realm of ergodic theory. So you don't need rates of equidistribution of the unstable. It's just a statement about long-term behavior, but with no quantitative requirements on them. So let's move to Bernoulli, maybe. So I'll maybe erase this. Yeah, and the Bernoulli property is trickier. So maybe I'll just tell you that a theorem of Rudolph, which is K non-Bernoulli in smooth setting. Which is just, what you do is you take Kalikov and you make it smooth. So what you do is you take something that you know is smooth and behaves like a shift. So you take, say, 2, 1, 1, so xy maps to, say, 2, 1, 1, 1 of x. Any hyperbolic would do here. And here you put g of tau x of y, where g is the geodesic flow. So gt is the geodesic flow. And your function now tau is mean 0. Tau acts from, say, the 2 torus to r, and mean 0. Yeah. So hopefully it's clear. I mean, one can see the analogy with this theorem, right? So you still put something which is essentially a shift in the base, and then you put something which behaves like a shift in the fiber. You need to put a flow, and you need a function that is R valued to make it. And of course I need to assume tau is not a coboundary, say. So this is the so this function has also the feature that you really grow like root n. If you look at the random walk, it grows like root n. So you want the same thing here. You want a function that grows. You don't want a function that's bounded. So that's why you assume not coboundary. And this was an example of Rudolph of a smooth one. There is one more that is due to Katok, I think. A different flavor, also skew products, which is you take xy maps to 2, 1, 1, 1, x. And then here you put ht cross ht. Well, okay, you put h cross h, tau x of y prime, where ht is a horocycle flow, is the horocycle flow. So you take the product, direct product of the horocycle flow, ht cross ht, and you. It's also to guarantee, I mean, in this case, I mean, if you put, yeah, because it decomposes, I mean, it's y in the second coordinate. Yeah, so you have, yeah, in this case, yes. And here, of course, always tau here is positive and not coboundary. And here it's different, right? Because here, if it's a coboundary, then you see it is not k because this guy has 0 entropy, the product has 0 entropy, and then if it would be a coboundary, then it would be a product of these two. Right, so I cannot, in this case, theoretically, I can take, I mean, I cannot, but I could take tau equal to 1 and still get a nice system that would be Bernoulli. Here, if I take tau equal to 1, I get a direct product of something that is hyperbolic and something that is parabolic, not hyperbolic at all. And it's a direct product, which means that the second coordinate is a 0 entropy factor, so it's not k. But Katok has shown, that's the interesting thing, that as long as tau is not a coboundary, then you are k. So basically, the only obstruction for being k is that, for not being k is the trivial one. Okay, so the. Yeah, so it should be a pair. Yeah, y and y prime. So you know, you need to take a product for reasons that I can't really mention. If you take one copy, it's trickier. We don't know what happens. I mean, sometimes we know, sometimes we don't. Yeah, but basically, you need a product. So the product, Marina Ratner has shown that this is not loosely Bernoulli. If you know what that means, this is kind of the main player to show not Bernoullicity of this example. Okay, but then if you want to talk about Bernoulli, again, in the interest of time, maybe I'll just draw you a picture what you need to do. So maybe I'll erase this. Yeah. So K means I take a single unstable leaf and I need to show it equidistributes. Now Bernoulli, there is something that I will not be able to discuss too much, Ornstein-Weiss reduction, which now tells you something maybe different. So now you take two unstable pieces that are close, say WUX and WUX prime, X and WUX prime. Yeah, and you want to find a map theta. So you want a map theta that depends on XX prime, such that the distance of Fi x and fi theta x less than some given epsilon for most I less or equal than n. So, okay, there is more quantifiers. Again, if I start to write all the quantifiers, it's going to be hard to probably continue, but given epsilon, there is an n such that for n much larger, I can find a map from one unstable leaf to the other unstable leaf such that the point and its image are close for most iterates up to n. So that's Bernoulli. Then if you can do this, if you can find a map, then F is Bernoulli. Okay, and you can see one instance of this where it's immediate to see what the map should be. So for example, if I take the 2, 1, 1, I take two unstable leaves. Yes, then there is this map, which is the stable holonomy S, which not only leaves them epsilon close, but when I iterate forward, so I is larger or equal than 0. And the points are actually getting much closer. So, sorry? Yeah, it needs, okay, I didn't mention this. It needs to be a measure preserving map, say, or epsilon measure preserving map. Yeah, thank you, of course. Yeah. You need to assume something about the map. Otherwise, I mean, yeah, anything would work. But yeah, it needs to preserve measure up to an error of size epsilon. So think of, yeah, again, something I don't want to define, but maybe you have a, yeah, there is an error, epsilon error, maybe here coming from the boundaries. But on majority of your space, the map is almost measure preserving. And here is the stable holonomy. And this is how people would show the Bernoulli property. So for example, one result maybe that I want to mention, theorem of Ratner, is that and also flows are Bernoulli. And the reason for this is for an Anoso flow, you also have two unstables, like this one and the other one, and then you have a section that is the center stable, CS. This is U and this is U, but the center is an isometry, right? So it's a flow direction. So if I start with points epsilon close, they will remain epsilon close, and if points start in the stable, it's never a problem. And this map is nice and absolutely continuous. Yeah, measure preserving, say. Well, okay, she assumed, okay, you need, so it's all, you usually assume K, so you assume that you need to have mixing Anoso flows, yeah. The question now, essentially, yeah, I should have mentioned this, is K property you assume, because if we cannot show K, I mean, there is no chance of studying Bernoulli, so we are always going to assume that, in this case, transitive or like mixing Anoso flows are Bernoulli. Yeah, and the proof is here, and now maybe what I want to say in the last 10 minutes is that essentially this is a very neat case where the argument applies, but if you think about constructing, so now think of a partially hyperbolic system which grows on the center. So here it was an isometry, here there was no center, so even better. But now think about a system that really splits on the center, and then this mechanism doesn't work anymore. So you need to do something else, right? So if there is growth, the points will split, and then who knows what will happen. Okay, and therefore, maybe the class of systems one could be interested in is you take, which already appears, I think skew products appear quite often, so you could take xy mapping to, and I'm just going to write 2, 1, 1, but this should be a nice uniformly hyperbolic system. That's the only thing that matters. And here you put something. You put a flow S tau x of y, where st is some flow. St is some flow. Some say flow, maybe ergodic, say. Okay, and then this is a nice and broad class of systems, and Katok tells you that if tau is not a coboundary, then it is K. So his result, the nice feature of his result is it's very general. But then you can ask, okay, depending on S, on ST, when is it Bernoulli and when it's not? Okay, and there are some partial answers already on the board, I think, in some cases, right? So this one, for example, tells you that if the fiber is very chaotic and the function has zero mean, so there are two features, well, I shouldn't, depending on ST and tau, I should say, right? And tau. So there are two somehow parameters that you have the flexibility to choose, and the behavior might be very different. So for example, if ST is the geodesic flow and tau is mean zero, then it's not Bernoulli. On the other hand, if this is a geodesic flow and tau is positive or has positive mean, then it will be Bernoulli. That's maybe an exercise. The result of Ratner, if you try to put it in that framework, gives you another result of Rudolph, for example. So Rudolph had one more, I mean many more, but in this setting, Rudolph tells you that if ST of x is just x plus T alpha, say, then let's call this thing F here. F is Bernoulli. So if you put a very simple elliptic dynamical system with no growth, like a circle rotation here, then kind of you're in the same, even though it's slightly different maybe setting, you're still in the same situation where you have isometry on the, so the center stable is isometry plus contraction. So you still can win. So generally what I want to do maybe the last 5 minutes, just tell you some things that are known on ST. And there is many that are not known yet. But basically now the question is, you see, if you put a highly chaotic fiber, like a geodesic or something hyperbolic, then you get Bernoulli or not depending on the tau. Here Rudolph doesn't have any assumptions on tau. Maybe, well, I always assume K. So, you know, we always assume this. Maybe, yeah. But, you know, there are many examples that you can put for which we don't know what happens. So let me give you some of them. For example, if we take 2, 1, 1, so, okay, the setting is this all the time. So I'll only specify S and tau. So if ST is the horocycle flow, then we don't know what happens, no matter what the mean is. Now, if you take, you can more generally, you know, this is a flow on a quotient of a simple, semi-simple Lie group, a parabolic flow. You can ask about more general unipotent flows. ST is, you can say unipotent flow. So, you know, higher on SL3R, SLNR, and so on. For example, you can put 1 T, T, 1, 1, T squared over 2, I think. This one would be an example on SL3. And then the answer is if mu of tau, so if tau has positive mean, has larger than 0 mean, then non-Bernoulli. And if tau has 0 mean, then we don't know. And this is kind of a obvious consequence of some results that we had with Kurt and with Darren, and then Darren with Elon. It's just about the fiber. So if you take this flow, it's not loosely Bernoulli, and then you reduce to the case that Ratner had somewhere. I mean, well, Katok theorem, it's the same thing. But he also needed tau positive. So for example, if you take the square of horocycle flow and you put mean zero function, it is not known. And maybe just two more, and I'll stop. So you can put, for example, you can put, for ST, you can put translation flows. So these are related to IET. And then it is Bernoulli. For integral of tau being 0. This is a result of Chang Guangdong and myself. Not known in positive, I mean, maybe under some extra assumptions, but we don't know if the mean is positive, generally what happens. And then maybe the last one I want to say is you put ST to be locally Hamiltonian flows. So these are flows on, I don't have time to really define them, so now, sorry, I'll just hand wave a bit. So these are flows on the surfaces which have some fixed points, and they are a bit like horocycle flows. And then we have an older result with Federico and with Kurt, saying that under some assumptions it is not Bernoulli, but, so, I mean, there is, okay, just one sentence. So if the exponent gamma, so, okay, is close to 1, whatever that means, then it is not Bernoulli. But actually, it turns out that if the exponent gamma is less than or equal than 1/2, then as student Mateusz, he has shown that it is Bernoulli, which is kind of a nice dichotomy in this set. Yeah, so I think it's time for me to stop.
So, any question?
What about nilpotent flows?
What about?
If you take nilpotent flow?
That's also a result of Rudolph. It is always Bernoulli.
Okay.
Because, but it's a completely different proof. It's just if you take, so Rudolph has this result. If you take a group extension of a Bernoulli, then it is Bernoulli.
Okay.
Nil flows are.
Anyway.